quantum mechanic problem questions. Let's give some a try. Let's start with this question. Let's start with this question. For the quantum number n is equal to 3, what values of L are allowed? What values of ML are possible, and how many orbitals are there? This is quite similar to the question that I did with you in the previous video when I went over the general layout and the foundation principles of quantum mechanics. It's just laid out a little bit differently so that you can have a better, so that you can test yourself if you really understood what I went over in that last video. You know what, I might actually even add a section here. What is the max number of electrons in this question as well? So let's actually add that there just to help supplement your learning. So we have the quantum number of n is equal to 3. So if n is equal to 3, what values of L are allowed? Well, we know that n minus 1 gives you your L value. Now, it's 0 up to n minus 1. So, n is 3. So this is our value here. So it's everything up to that point, up to this value of 2. So L could be a 1, and L could also be a 0. So what values of L are allowed? Well, it's pretty obvious. This is allowed, and this is allowed. That's the answer for that. What values of ML are possible? Well, as we can see, ML is 2L plus 1. Again, if you have no idea what I'm doing here, you should probably see the previous video of the foundation principles before you follow along here. So 2L plus 1. So we get 2 times 2 gives you 4, plus 1 gives you 5. Our ML value is here as well. 2 times 1 gives you 2, plus 1 gives you 3. And here 2 times 0 gives you 0, plus 1 gives you 1. Now, these numbers here are the number of orbitals. It's not the actual value. I know the question is asking for what values of ML are possible. So these are not the values. This would not give you the correct answer on a test. These are the number of orbitals, and then from there we're gonna dissect what the value is. So if this is 5, this means that there are 5 orbitals. The value of it is this rule: negative L to positive L. So if there are 5 orbitals, and we know that can be going from negative 2 to positive 2, this means this is negative 2 all the way up to positive 2, and then everything else in between tags along. These are your values: negative 2, negative 1, 0, 1, 2. Similarly, your ML value is here, 3 orbitals, negative L to positive L, so negative 1 to 1. And then last one here as well, 1 orbital, and then of course it can only just be a 0. So what values of ML are possible? So the values of ML can be 0, it could also be negative 1, it could also be 1, it could also be negative 2, and it could also be positive 2. That's pretty much the answer. Lastly, how many orbitals are there? Well, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the answer for that. Lastly, what is the max number of electrons in this question? 1, 2, 4, 6, 8, 10, 12, 14, 16, 18. Again, very similar to the answer that I gave in the previous question during the foundational understanding of quantum mechanics in the previous video. This was just laid out differently, so hopefully this starts to make more sense and supplement your learning from the last video. So that is the first question. Let's try another question. How many orbitals are associated with each of the following types? Now it's important that we understand what these values that you see in front of you, what do they actually mean, okay? So we're gonna have to see what the heck does 1s mean. Well, 1 means the principal quantum number, so n is equal to 1. S, what the heck does the s mean? Remember this, L is equal to 0, L is equal to 1, L is equal to 2, L is equal to 3, and 0 represents the S, L is equal to 1, the P, the D, and the F. Remember all of this? This was relating to the block, the subshells. So that's what this S is representing. It's representing the subshell S. So what is S? L is equal to 0. So we're just going to match that over there. All right. How many orbitals are associated with it? Well, it seems as if this one follows the n minus 1 quite well. 1 minus 1 gives you 0. Good. And then the ml is going to equal 2 times 0 plus 1. So that would just give you 1. So how many orbitals are associated? Well, there's only one orbital. And what is the value name associated with this title? 0. All right. So that is A. Now let's do B. 5F. All right. Again, 5. N is equal to 5. F is over this. L is equal to 3. Now, this doesn't follow the n minus 1 rule. 5 minus 1 does not give you 3, but remember, it's 0 up to that value. So 3 can be there because it could be L is equal to 4, but remember, it's 0 up to L is equal to 4, right? This 4 here is from that rule, n minus 1, but it's not limited to that. It's 0 up to that value, so 0 up to 4. So everything from 0 up to 1, and then 2, and a 3, and even a 4. But L is equal to 3, which exists here, so it's valid. Now, let's just continue going on. ML is equal to 2 times your L value, which is your 3, plus 1. So you end up getting 6 plus 1 gives you 7. So what do we have here? Well, you have 1, 2, 3, 4, 5, 6, 7. Hopefully this is making a little bit more sense now that we're putting all of these kind of as an example. All right. So there are 7 there. What are the, I wouldn't say names, but the ML title values for every single one? Well, if there are 7, we've already listed them out. We know that L is equal to 3, so it needs to go from negative L to positive L. So we get negative 3, negative 2, negative 1, 0, 1, 2, 3. Hence, these are the value names. How many orbitals? 7 of those. All right, C. 4F. So N is equal to 4. L is equal to what? Well, F is that value of 3. And this follows that quite strictly, n minus 1. Okay, which is fine. And then, which is great actually. So then ML is equal to 2 times 3 plus 1. All right, so 3 times 2 gives you 6, gives you 7. All right, so it's following this thing again. It's giving us 7 orbitals again. So 1, 2, 3, 4, 5, 6, 7. Again, we can list them down here, the names here, but it's not really pertinent to the question. And then the last one, we get 2p. Again, n is equal to 2. What is the p value here? Well, p in the block is L is equal to 1. So L is equal to 1. Okay? Well, ML is equal to 2L plus 1. So 2 times 1 gives you 2, plus 1 gives you 3. So you get 1, 2, 3. Therefore, you get 3 orbitals. All right, let's move on to another question. All right, next question. What sets of quantum numbers are possible for 4D orbital? Now, it says sets of quantum numbers. It's not asking you for a specific ML value or L value, if it's valid or not. It's asking you for a full set of quantum numbers. Remember, the quantum number, the model that we're trying to do, so the quantum model, we need to list it out as the numbers. Okay, so the numbers represent the model of what we are looking at, of the element in question, for example. So we need to list them all down. Remember, we're not doing Bohr. We're not doing Bohr anymore, okay? which means we need to write down the actual value specifically, like a postal code, right? If n is equal to 5, okay, then what? We'll just do a strict n minus 1. So 5 minus 1 gives you 4, okay? And then our ml value is equal to 2, right? So 2 times whatever value is here, right? So 2 times 4 gives you 8, okay? Plus 1 gives you 9, okay? So we could be doing this kind of postal code specifically for our quantum model. So we're not going to be doing the Bohr method. Okay, this is a lot more specific. All right, what sets of quantum numbers are possible for the 4D orbital? So let's try the 4D. So if n is equal to 4, and our d value, remember, don't forget all of these. L is equal to 0, L is equal to 1, L is equal to 2, L is equal to 3. So the S, P, D, F, where is the D? L is equal to 2. So L here is equal to 2. Now, we also got to do our ML values. Well, our ML is 2 times 2, right? Plus 1. Hence, it gives us 5. Well, let's write it out. 1, 2, 3, 4, 5. And let's associate it. Okay? Remember, negative L to plus L. So negative 2 to positive 2. So we have negative 2, negative 1, 0, plus 1, plus 2. And again, these are the electrons. If filled, would look like that. Now, let's list possible quantum set numbers. Well, first one could be n is equal to 4. That's not all. N could also equal, L could equal to 2. These remain fixed because it's the 4D orbital, so that cannot change. What does our ML value be? Well, our ML value can be any of these. It can be all of them. So let's just start with one of them. Let's say it's negative 2. All right? So, if that's the case, why do we pick negative 2 instead of negative 1 or 0 or 1 or 2? If you're thinking that, you're right. We could do those. So n is equal to 4, L is equal to 2. Again, that does not change. Okay? Depending on, it's like where you live, right? If this is Canada, let's say this is Ontario. Okay? Obviously, it does not change. Okay? But this, if you're moving around within the city, that can change. So n is equal to 4, L is equal to 2, ML is equal to, let's say, negative 1. Or we can do n is equal to 4, L is equal to 2, ML is equal to 0. We can also do n is equal to 4, L is equal to 2, ML is equal to positive 1. We could also do n is equal to 4, L is equal to 2, ML is equal to plus 2. Again, so if you're moving around within your city, whatever city that you're living in, that would be your ML value. And we can list those. Okay, one address of city here, one address of city here. Okay, but let's say you never left Canada, Ontario. So that means this here, your Canada, this here, your Ontario, does not change because you've never left. You're moving around locally, but you're not moving around internationally. Okay, so you're fixed here, and you're fixed here. You're fixed in the country, you're fixed in the province. But you can move around here because these can change because they were not listed over here within the question. So all of these here could be possible. So this is your answer. Let's try another question. All right. Next question. Which of the following sublevels does not exist? Let's give it a try. Well, we have our 5F. How do we know if this exists or not? Well, n is equal to 5. Then what do we have to look at? We have to look at our L value, okay? So this here, again, has our N value and our L value. What would be our L value? Well, as you can see here, we need to have N is minus 1. Well, N minus 1 gives you 4. So if that's the case, that means ML will just be 2 times 4 plus 1. Now, if you want to take this route, you can, but what is a lot better is if you try this this L value here becoming 3, okay, and then our L value becoming 2, L value becoming 1, and L value equaling 0. This could all work as well if you want to take it this route faster. So we can get our ML values for every single one of these. Now we just have to make sure that this works out. So if we have our L is equal to 0, L is equal to 1, L is equal to 2, and L is equal to 3, S, P, D, F, well, our 5 here, okay, is a 5F. So N, it would equal to 5, but the F, as you can see here, L is equal to 3. Okay, so L is equal to 3. That would be this one over here. All right, remember, 5 minus 1 can give you 4. But remember, it's 0 up to that value of n minus 1. So 0, 1, 2, 3 precedes 4, so this would still stand true. So you can do it that way. So this one would work out. So this does work, so it is possible. All right. Next, we can try 4f. Well, if n is equal to 4 and L is equal to what? Well, L needs to equal 3. Does that work out? Well, let's give it a shot. If it says L is equal to 3, that means this here is a strict n minus 1, which is good. So anything up to that value, 0 to n minus 1, so up to 4, can work. So because this is specific enough of n minus 1, this is obviously an automatic check mark. Next, we have our 2D. So let's try a 2D. Well, if we have 2D, n is equal to 2, but how about our D value? Well, L is equal to 2. All right, so does that work out? Well, 0 goes up to n minus 1. 2 minus 1 should give you 1. So we're limited to just 0 and 1. However, look at our L. It's 2. It exceeds this 1. This is our limit. We cannot go past that number. We've already established L is equal to 2, so this is not possible. So it seems as if 2D is going to be our answer. But let's just keep doing the rest just in case. 2P. If n is equal to 2, and P here, we don't know what it is. We look up here, we know that L is equal to 1. This follows a strict n minus 1. We don't need to do a 0 to n minus 1 now analysis. So what we can do here is just look at it, cross-reference, and it makes sense. So it works out. Last one is your 3D. Seems like we're heading into good water. 3, n is equal to 3. L is equal to what? D is L is equal to 2. Does this work? Yep, it's a specific n minus 1 of 3 minus 1 gives you 2. This works out. Definitely 2D here is the answer. It does not exist. Let's try another question. Which group exhibits the electron configuration ns to the power of 2, np to the power of 4? Well, let's have a look at our questions. Well, A is a pnictogen. Well, the pnictogens are over here. These are the pnictogens. Now, why are they over there? Well, we should know that pnicto stands for poison and gin just stands for producing. So these are the poison producing ones. Okay, so nitrogen, nitrogen is everywhere, right? It's about 78-79% of the air that we breathe, but it's with the presence of oxygen. If there was no oxygen at all, then it would be extremely poisonous. All right, phosphorus, again, all of these are pretty bad. All right, let's look at the pnictogens. Our NS2, remember, this here was our block. This was our S block. There are 2 electrons. Remember, these are the columns. So if we have 2 over here, it is pretty much all occupied. So we can move on to our P4. Okay, remember N. Okay, these are the ones that we just don't know. So P4, we're going to skip on to the P4. Well, this is our P block, so let's look at our P block here. All right, 4. 1, 2, 3, 4. All right, so that means orbitals are filled this way. 3, okay? And then, of course, all of them must be filled, half filled before we can start double filling. So this would be our subshell, our last subshell. So this here would look like oxygen. So this would have to be the answer, right? Our chalcogens is our answer. Now, let's try out the other ones, okay? Because if we use the pnictogens is when you get rid of this all the way up to here, only up to there. So let me show you again. Again, this is our P block, all right? If we stopped at our pnictogens, then it would be 3. So this would be a P3. We're not there yet, okay? We got to get to a P4. So our chalcogens would be our P4. All right? If we did another analysis, okay, so we already know that this is correct, but if we did an icosagen, right, which is just the boron family, okay, it comes from the icosahedron. The shape had 20 sides. Okay, that's what the boron would look like. The element boron has an icosahedral shape. So the icosahedrons, 1, 2, okay, this is already all filled up. But because it's in the P block as well, over here, the icosagens, if there was just one over here, then this would just be the boron family. So this could not be correct. If we did the halogens, if we went all the way up to the halogens, okay, 1, 2, 3, 4, 5, then there should be 5 over there. So 1, 2, 3, 4, 5. So it can't be that one because that's where it ends off. We need to end off right over here. So it can't be that. The tetragens, again, the tetragens would look more like 1, 2, 3. Okay. So if we had, let's say, a carbon, right? Carbon is a 6. So we had 1s, 1, 2, 3, 4, okay, 5, 6. So we got to get rid of that one. All right. So this here is our carbon, right? Because it's part of the tetragen group. So this obviously can't be right because it ends off over here. We need our P's to have 4 electrons. This P only has 2 electrons. If you add in another one, you get your P3. Okay, and if you were to count them all up, 1, 2, 3, 4, 5, 6, 7, okay, 7 electrons, that would be your nitrogen. So nitrogen has 7 electrons. So that would work out. However, if we did our tetragen, like we just did, 2, 4, 6, right? 6 electrons. That would be carbon, 6. Remember, we need to get P4. This is only P2. So the P3 is obviously incorrect. Our P4, what we just did right now, is incorrect. We need to add 1 here as well, and 1 here as well, because we need 2 here, we need 1 here, and 1 here to add up to 4. So if you were to count them all up, 2, 4, 6, 7, 8, that will give you 8 electrons. So that would be oxygen. So oxygen here would be that family. So that's how to prove it in long layman's terms, but hopefully you understand the concept.